One of the questions that I get a lot is, what's the difference between continuity and differentiability? And in fact, in one of the previous videos, I've shown you that if a function is differentiable, then automatically it's also continuous. So it's natural to ask, does that go the other way? If you're continuous at a point, do you have to be differentiable at that point? And the answer is no, and I want to show you that now. So there's a specific function that is a really classic example of this. So let's make our function, let's call it y equals x times sine of 1 over x. And that's going to be the case whenever x is not equal to 0, because you can't plug in 0 here to sine 1 over x. And when x is equal to 0, let's just call it equal to 0. And so I'm going to show you that this function is continuous, but it's not differentiable. So how can I show you that it's continuous? I need to show you that, or continuous at 0, I need to show you that the limit of x times sine of 1 over x goes to 0 as x goes to 0. And this is a great opportunity for me to use the squeeze theorem to show you that. Now, so how can I set this up? Well, the first thing I'm going to notice is that no matter what I plug into sine, let's look at sine 1 over x. The y values have to be less than or equal to 1. They have to be bigger than or equal to negative 1. And so the next thing I want to do is I want to multiply this inequality all the way through by x, or to give me x times sine 1 over x in the middle. So I'm going to get minus x. It's less than or equal to x times sine of 1 over x is less than or equal to x. Now, if x is positive, you can do that multiplication without switching the inequalities. If x is negative, then it's true that both these inequalities get switched. But it still turns out to be the same. It still turns out to be this inequality, just written a little bit differently. So this holds true no matter whether x is 0, positive, or negative. We have this inequality. So if you remember that squeeze theorem, we've got three functions, negative x, x times sine of 1 over x, and x. They satisfy an inequality. So the next thing I have to check is it true that these two functions have the same limit as x goes to 0? Well, absolutely. The limit of x as x goes to 0, it's equal to 0. Limit of negative x as x goes to 0, it's equal to 0. And so now the squeeze theorem says this function that's squeezed in the middle, its limit has to be also equal to 0. It has no choice. And that tells me that the limit of f of x as x approaches 0 is equal to f of 0. So that tells me that this function is continuous. So the next question is this function differentiable at the point x equals 0? And the way that I can try to figure that out, there's basically no way to figure that out other than just plugging into the definition. So that's my y equals f of x. So the definition of differentiability tells me you're differentiable if this difference quotient limits to something, if the limit exists. So the difference quotient is h goes to 0 of f of x plus h, but I'm taking the derivative at the point x equals 0. So I'm going to get 0 plus h minus f of 0 all over h. That's the definition of the derivative at the point 0, right? And so plugging this in, when x is equal to 0, the y value is equal to 0, so that's just 0. Now when I'm plugging in h into the function, that's just going to give me h times sine of 1 over h, and then subtracting 0, divided by h. And so that's going to be nothing but the limit, canceling out the h's, it's going to be the limit as h goes to 0 of sine 1 over h. And so this function is differentiable if that limit exists. But that limit definitely doesn't exist. The limit exists if these y values are approaching a single number as h goes to 0. But if you look at the graph of sine 1 over h, it gets pretty wild as h goes towards 0. I'll try to sketch it for you a little bit. So schematically, what happens is you look like the usual sine curve. But then as h goes to 0, that's like squeezing in a lot of domain, really close. So the frequency gets huge. You're always oscillating between -1 and +1. But the frequency gets out of control. So the y values are definitely not approaching a single number as h goes to 0. So this limit does not exist. So the function's not differentiable, but it is continuous.